In 10.8, they're going to throw something that literally has direct applications into calculus and into physics. Sometimes people wonder, when am I ever going to use this in real life? And I always think that this is the kind of mathematics in this section that is going to be used not just in this math class, but in next year's math class and even the one that follows it. So if you are a freshman or a sophomore in this class, this is something you could see if you plan on staying in math for the next 2 years. You will see this kind of math all the way up even into calculus. With that being said, the concept that we're going to be dealing with is something called the average rate of change. The rate of change tells how much the graph is changing by, otherwise known as the slope. And if you're wondering, like, how does this really apply, what we're going to do, I just want to give you the calculus idea because I think you're smart enough to understand it. I literally think everybody in this room can understand. If I had something that went up into the air and then starts coming down, that's what a parabola looks like. An object follows this path, assuming there's no wind, assuming there's nothing else other than gravity affecting the object, like a ball thrown in the air. What happens is the amount of change that happens as the object goes up is that gravity keeps pulling this object down and down and down, and then it slows down. It no longer is traveling upwards, and then eventually the object starts accelerating downwards because gravity accelerates objects at a certain speed. This rate of change is used in calculus because we can figure out what something called a derivative is and how the derivative is related to the object's speed. That this position and the derivative of position is velocity and things like that. So basically, we're not going to go as far as calculus and learn the velocity of objects. What we're going to do is we're just going to try to figure out how much is it changing from this point to this point, or how much is it changing from this point to this point, or how much is it changing from this point to this point. That's what we do in this level. If you wonder what do they do in future level math, they don't calculate it as an average. What we do in this class, let me fix this real quick. What we do in this class is we find the average between 2 points. In calculus, they find it instantaneously at a single point. We have to find an average, whereas in calculus, they can find at the exact moment in time using a different type of math called a derivative. That's future for you. So what do we do in here? We use something called the slope formula to find the average. It's the difference of your y's subtracted by the difference of your x's. y2 minus y1 over x2 minus x1. These 2's and these 1's are just telling you that this y is your second y minus your first y. They have nothing to do with the problem other than it's your second y minus your first y divided by your second x divided by your first x. In my previous point, if I'm finding the average between this point and this point, this might be my first x and my first y. This might be my second x and my second y. What we're going to do is we're going to subtract the y's divided by subtracting the x's. We just have to make sure we're going from either left to right or left to right in both places. We cannot go y2 minus y1 and x1 minus x2. That would be going left to right and then right to left. We want to make sure we're going in the same direction. Okay? So this slope formula is something you're going to use, and that's with a graph. But sometimes you won't be given a graph. Sometimes you're going to be given equations. And because you're given equations, you might want to think of it as output 2 minus output 1 divided by input 2 minus input 1. And I say that because they're going to use a whole lot of function form on these two worksheets that I gave you. I gave you a notes worksheet and I gave you a homework worksheet. When they give you an equation that's in function notation, you haven't seen this since last year in Math 1. So I wanted to show it to you because if you have a function notation and it says f of x is equal to x squared, don't think that this is f multiplying x. This is just the name of the function. This is the same exact thing as saying y is equal to x squared. But the reason that they do not put a y in that spot is so that they can tell you a difference between this function and this function. This function is called f of x. It's the one that has the x squared. This function is called g of x. It's the one that has 2 to the x. They're different functions. They both have a y value, but the equations are different. And instead of using like a y2 and a y1, they just named them differently. And so we're going to use function notation because sometimes we're going to have to figure out when x is a certain value, what's the y? And I'll use that notation as we get into it. And this is the most important thing that you'll probably end up doing. If I need to know what the output is, when x equals 1, sometimes you're going to have to plug that into your equations and figure out, well, what is the output when you have 2 to the first power? You're going to figure that out. That's your output. This is your input. Sometimes that will be different depending on your equation. That's the whole nature of this worksheet, okay? So my plan right now is not to do anything on the worksheet portion of what I passed out to you. My plan right now is only to go over a few problems on the notes worksheet with you, and then by the time we're done going through the notes, you should know how to do the worksheet on your own. This should look just like the same thing that I just passed out to you. Doesn't have some numbers on this graph, but I'm going to put them down anyways. When time is 1 second and 3 seconds and 5 seconds, it's kind of missing there, so I'm going to put those down. And if this is 2 and that's 4, then this dot's probably at 5. 8, 9, 10, that's probably at 10. 12, it looks like it's at 13. 14, this looks like it's at 15. 16, that looks like it's at 17 and maybe 18 possibly. And so I do that because it says use the graph to estimate the distance the car has traveled at 1 second. What they're asking you is if I go 1 second, what's the distance that this car has traveled? It has traveled how many centimeters? It has traveled 5 centimeters, so we just put 5 centimeters in there. 3 seconds, how far has it traveled? If you look at that, I'm thinking it's about 13 centimeters. It's fairly simple, right? 5 centimeters, it has traveled about 17 centimeters, and that's the first part of this question. If you're looking at how this object is slowing down, you can imagine that somebody pushed this object kind of sort of up a hill. Or maybe they pull, I don't know, remember if those little cars that you pull back and then the springs, you let it go and it just goes on its own because you've tightened the spring and it goes up it just goes. If it goes up a hill, it will start to slow down. That's what this is. It's slowing down. It's not going as fast and covering as much ground. Then, this is what the major idea of the question is. What is the average rate of change from 1 second to 3 seconds? From here to here, what is the average rate of change? They don't give you a formula. You're supposed to know. So then we go back up to our notes. How do I find it? We do a y2 minus y1 over x2 minus x1. This is your input. Think of this as your x1. Think of this as your x2. Which means if this is your input, your output, this must be your y1, because that matches with the 1 second. And for the 3 seconds, this must be your y2. You're going to take what was the distance traveled and you're going to subtract them. 13 minus 5. And believe it or not, I'm going to erase that. I'm going to put 13 centimeters minus 5 centimeters for a specific reason. And 13 was my y2 minus y1. I have to do x2 minus x1. I have to do 3 seconds minus 1 second. It said make sure to include units. That's why I put the units in there. I want to make sure I'm answering the question. So now that we have 13 centimeters minus 5 centimeters, that makes 8 centimeters over 2 seconds, which reduces. What does it reduce to? It reduces to 4 centimeters per second. Let's box that as my answer. What you have calculated is from 1 second to 3 seconds, you're finding the average speed, the average velocity. That's what we can do in Math 2. In calculus, you wouldn't find an average. You would find the instantaneous, totally different idea. And sometimes this speed changes. What is the average rate of change from 3 seconds to 5 seconds? Well, guess what? This is your first x. That's your second x. I erase these two things over here. If 3 seconds is my first x, then this must be my first y. And 5 seconds is 17. That must be my second y. How do we find the average rate of change? We do the difference of y's. 17 centimeters minus 13 centimeters divided by 5 seconds minus 3 seconds. And we're going to be doing this a lot, so let's just get used to it. 13 centimeters minus 3 centimeters is 4 centimeters over 2 seconds. That reduces. 4 can be divided by 2. 2 centimeters per second is my answer for number 3. So what I want you to think about, because the big idea is the average was 4 centimeters per second, and then between 3 seconds and 5 seconds, the average is 2 centimeters per second. What that tells you is it slowed down. It didn't travel as far. Those are ideas that you're going to have to play with the average rate of change. What do the answers to questions 2 and 3 tell you about the movement of the car in 2 different time intervals? It was traveling at 4 centimeters per second. Now it's traveling at 2 centimeters per second. In summary, it is doing what? It's slowing down. If you want to be real specific, you would say its speed reduced by 2 centimeters per second. But I don't think that's what it's asking. It's just what can you tell about the movement of the car? The car is definitely slowing down. Now this is where I wanted to get into. I wanted to get through all of 5 and 6 with you, and then I have some numbers that I want you to punch in for number 7, and then we'll be done with your notes. But this is that function notation that they use. And some of you have not seen this because I know it's not in any of my curriculum in Math 2. So you haven't seen this since last year in Math 1 or in Math 8 for some of you who came from Math 8. Okay? What is the average rate of change of f of x from x equals 1 to x equals 3? And they're asking you to check this for f of x. Now if you go to f of x, there's this whole chart. You don't know what the y values are until you calculate them. So these are your inputs. They want to know what is the output. If I have x is 1 and you were to plug 1 into that equation, you would have 1 squared. What is 1 squared? Simplify it. You put it in the chart. If you have a 2 and you plug it in and you have 2 squared, what is 2 squared? You simplify it, you put it in the chart. 3 squared, 4 squared, 5 squared. If you don't know what those are, use a calculator. 3 squared is 9, 4 squared is 16, and 25. Because we're plugging them in to f of x. Then I have to do the same thing for g of x. I have to plug in those values. Thank you. So if I do 2 to the first, or 2 to the second, or 2 to the third, or 2 to the fourth, or 2 to the fifth, these are going to be different than these ones. These are all squareds. These are all 2 to the first. Well, let's see. 2 to the first is 2. 2 to the second is 4. 2 to the third, 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. It's 32. If you don't believe me, use a calculator. Double check that. I'm plugging in the values into those functions. Then they ask me for the rate of change only of f of x. I go to f of x. They tell you, here's your first x, here's your second x. If you're going over to your chart, this is your first x, this is your second x. This must mean that this is your first y, this is your second y. I'm just kind of putting them over there because that's what I have to use to figure it out. So I'm going to do y2 minus y1, y2 minus y1, 9 minus 1, over x2 minus x1, which is 3 minus 1. 9 minus 1, 8. 3 minus 1, 2. The average rate of change is 4. What is the average rate of change of g of x from 1 to 3? Well, they're telling you this is your first x, this is your second x. They want you to know, well, this is your first y and this is your second y. I label them because that's what we're going to use. So then what I do is I do y2, 8, minus the other y1, 8 minus 2, over 3 minus 1. Simplify, 4 over 2. My average rate of change is 2. Part C says the average rates of change are different. What does this mean in relationship to the graph? In f of x, it makes this kind of function, and we're figuring out what that average is. Did I mess up on something?
8 minus 2 is 6.
Thank you. Thank you. That helps. It helps a lot. Simple mistake. Thank you for paying attention. My second period class is paying attention, and they're fixing my mistakes. I appreciate that. Okay. Good job. So now, what does it mean, though? That the average rate of change of this x squared graph has a steepness or a rate of change of 4, up 4 over 1. Whereas this 2 to the x, I don't know if you remember this from Math 1, but 2 to the x is an exponential graph that looks like this. So what do you think that we have figured out? This is a change of up 4 over 1. This is up 3 over 1. What does this mean? It means that f of x is steeper. It's changing faster. G of x doesn't change as fast, right? It's not as steep. And then guess what they do? They ask you to find the average rate of change of f of x, and they ask you to find the average rate of g of x, but now from 3 to 5. So that means because they're telling you this input and this input, you're going to have to use different y's. Now I'm going to just jump right to it without labeling anything because I think you're ready for it. If we're using the 5 minus 3 on bottom, 5 minus 3, or x2, it's going to be 25 minus 9 on top for f of x. Please double check my math. Now you guys have me thinking, did I do the math right? I'm going to do the same thing for g of x. G of 5 is 32. G of 3 is 8 over 5 minus 3. 24 over 2. 12. But then something funny happens. From 3 to 5 on f of x, where this was steeper and this was not as steep, 3 to 5, this one has 8 and that one has 12. This one's steeper now. G of x is actually going to become steeper than f of x. So something happens between those two graphs. One, the exponential starts becoming more steeper, believe it or not. So let's say g of x becomes, bless you, steeper, bless you, than f of x. And how do we know that it's steeper? It's because this has a higher rate of change. It's changing more. That means that the graph is steeper. When I think about like, how much is it changing by? So this is the basic type of math that you're going to do throughout all of the worksheet. Now I don't feel like you should have to do all the calculations on number 7, so I'm going to give these to you. Here's the deal. They're going to ask you, what's the average rate of change between 0 and 1? You'd have to do this y minus that y, this x minus this x, but I decided I'm just going to give that and do all those calculations for you. So here's what I'm going to do. Let me zoom in on this. Why don't you write those things down and just fill in your chart. And just a little preview as you're writing those things down, there's going to be something different about a linear graph, a quadratic graph, and an exponential graph. That's what your last section is on anyways, in section 9. So as you look at these, something different happens for the average rate of change of a linear graph versus a quadratic versus an exponential. And I've done a lot of the questions with you. The only questions I have not done with you are 8, 9, 10, 11, 12, 13 on this worksheet. I think after you have these things down, you should be able to answer the questions. I'll do number 8 with you. What do you notice about the average rate of change for the linear function? What do you notice about how much is this changing from one to the next and one to the next? It stays the same. What do you notice about the average rate of change for the quadratic function? Do you see any patterns? It's changing. It's getting bigger. Do you see a pattern? Goes up by 6. It increases, is a fancy word. It increases by 6. units each time. That's neat. Number 10, what do you notice about the average rate of change for the exponential function? Ooh. It doesn't just increase, it multiplies. By what? Oh, I'm not spelling that right. That looks right. Multiplies by 3 units each time. That means that this is going to eventually become way steeper than this because it's multiplying, not just adding. It increases by 6. So I'm going to let you do the rest of this stuff on your own. I hope that gives you a clue as to what you're supposed to be doing. I'm going to stop your notes right there.